Equations and word problems are telling us a series of steps that happened to a number. So we start with maybe an unknown quantity that we decide to call x, and a series of things happen to it. When we are trying to solve this equation, we're trying to go backwards to figure out what x was before all these things happened to it, right? Start off with a number, any number, and add 3 to it in your head. Take that number and times it by 2, and then take that number and subtract it by 7. And now you have some number. And if I want to go backwards in time, I'm going to take this equation. We started with x, we added 3, we times it by 2, we subtracted 7, and now we end up with some amount, some unknown amount. Maybe you ended up with 28. So if you ended up with 28 and I want to figure out, okay, what number did you actually start with? I need to go backwards through your problem. So I know the last thing you did was subtract 7. So before you subtracted 7, you had 7 more than this number that you're ending with, right? So in order to undo that subtracting 7, I'm going to add 7 to the number you ended up with. And that's going to tell me what you had before you subtracted 7. Now I know before you subtracted 7, you multiplied everything you had by 2. So if I need to get rid of that times 2, I'm going to do the inverse of timesing by 2. I'm going to divide by 2. Multiplying and dividing are inverse operations. So that'll cancel out the timesing by 2 that you did. And then the very first thing you did was you added 3 to your number. So I want to subtract 3 to get back to whatever you had before you did all 3 of those steps. So if you gave me your ending number, I could add 7, divide by 2, and subtract 3. That would undo all the steps you did and get me back to the x that you started with. Whenever we're solving equations, we're going to use these principles to help us go backwards through equations to figure out what we had to start with. And in order to do that, we're going to use inverse operations. Just as a quick reminder, we are going to use adding and subtracting as inverse operations. Adding 2 and minusing 2 are opposites of each other. We're going to use multiplying and dividing. And there's other inverse operations you can use too, in more advanced ones. If you had a squared to the power of 2, you could undo that with a square root. We're not going to need those today. So let's do some examples. We have some number minus 11 leaves me 20. Now you might right now know this solution in your head, but just to show you how we're going to solve it, I'm trying to end up with x equals something, just all by itself. I want to get x alone in this equation. So in order to do that, I need to get rid of this minus 11. So I'm going to add 11, my inverse operation, to both sides. When I do that, I'm going to make sure I really recommend drawing this line through the equals so that you can make sure you're adding 11 to both sides of the equation. Think about an equation as being balanced. On one side of this scale, we have x minus 11, and on the other, we have 20. And right now, it's perfectly balanced, we know, because it's equal. So if I wanted to add 11 to one side, I have to add 11 to the other side so that this scale doesn't get imbalanced. It will make it not true anymore, right? So negative 11 and positive 11 cancel right out. We're left with x. And on the right side, 20 plus 11 leaves me 31. So nice. X is already all by itself. X is 31. Double checking. 31 minus 11 is 20, right? All right, we're going to solve this one 2 ways. The first way we can think about is we have 15, we subtracted x, and we end up with 9. So to go backwards through that problem, I'm going to get rid of that minus x first. So I'm going to go ahead and add x to both sides of this equation. This does not have to be your first step. It's just one way to solve this. When I do that, I have 15 and 9 plus x. 9 plus x is kind of a pain though, because I can't simplify that anymore. So I'm going to have to get rid of that 9. It's a positive 9, so I'm going to subtract 9 on both sides. And I end up with 6 and x. X is all by itself on one side, so we're done. We know that 6 is x. The other way you could solve this, though, is you can start by just trying to get x by itself on the left side. It doesn't matter, we're going to get the same answer, but it's another way to do it. So I need to get rid of this 15. It's a positive 15, so I'm going to subtract 15 on both sides of the equation. I have 9 minus 15 is negative 6. And on this side I have, be careful, this is a negative x. Make sure you bring down that negative sign with you. Now, negative x, remember, is we have a little invisible negative 1 right in there. And so if we want to get rid of that, we're going to divide by negative 1 on both sides of the equation. Negative 6 divided by negative 1 leaves me positive 6 for x. Same answer, right? Just two different ways to solve. There's so many ways to solve. But let's talk about that negative x really fast. So just as a reminder, 15 minus x is exactly the same as 15 plus negative x. You can think of it as a negative x or a subtracting x. They're exactly the same. But when you bring it down, remember to bring that negative with it. Whether in your head it's a subtraction or a negative sign, bring it with. All right, 15 plus x is 23. We need to get x all by itself on one side, so I'm going to get rid of this positive 15 by subtracting 15 on both sides. So my 15's cancel to 0. I have x equals 8. How nice, we're done. Here we've got x minus 3 is negative 2. So before I subtracted that 3, I had something that was, 3 bigger. So I'm going to add 3 to both sides of this equation and double check that the negative 3 and that positive 3 are canceling each other out. And x equals negative 2 plus 3, which is 1. Double checking. 1 minus 3 is negative 2. All right, 3 times x equals 42. We need to get rid of that times 3. Remember, there's a tiny little invisible times sign right in there. So we're going to divide by 3 on both sides. Just an important side note here, whenever you are multiplying or dividing in an equation, you have to do it by every single term in that whole equation. Not super relevant here when we only have one term on each side, but you'll see what I mean as we go on. So 3x divided by 3. My 3 divided by 3 cancels because it's just 1. And 1x is just x. On my other side, 42 divided by 3 leaves me 14. And we're done. X divided by 5 equals 14. So we need to get rid of that divide by 5. In order to do that, we're going to need to multiply by 5 on both sides of this equation. So the 5 and the divided by 5 cancel out to 1, and I have x equals 14 times 5 is 70. Double checking. Is 70 divided by 5 equal to 14? Hope so. All right, when you see fractions, we're going to not panic. We're going to do exactly what we've been doing this whole time, just with a fraction, right? So we had plus 1/2. We're going to need to subtract 1/2. We're going to do it on both sides of the equation. And we're going to remember that you cannot add and subtract fractions unless they have common denominators. So I can't subtract 3/4 and 1/2 until they have common denominators. Luckily, it's really nice to do this one because you can turn a half into fourths very easily. So this becomes 3/4 minus 2/4. So x is equal to 1/4. X minus 7/8 equals 5/2. To undo this, we're going to add 7/8 to both sides. And then we're going to again need common denominators before we can add these two together. So we have 5/2 and 7/8. It's easy to do 8 as a common denominator here. I mean, you could do 16, you could do 40, but it's not hard to do 8, so we'll do that. So we've got 28 plus 7/8 makes 27/8. When your problem is already in an improper fraction form, like we have up here, you probably can leave your answer in an improper fraction too. And if you're in my class, you can definitely do it because I love improper fractions. But if it's important to you or important to your teacher to make it a mixed number, we can do that. 8 goes into 27 3 times. And then we have 3 times 8 is 24, 25, 26, 27 is 3 extra little eighths left over. 2/3 times x equals 8/9. I'm going to solve this 2 ways. So the first way is remembering this as just 2 times x divided by 3. And we're going to undo each step by itself. So to undo the divide by 3, I'm going to multiply by 3 on both sides. That leaves me with just 2x on this side, as 3 divided by 3 cancels. And I have 24/9 over here. 8 times 3 is 24. And there's, that invisible 1 on the bottom. I've got to divide by 2 now to get x all by itself. So I have x equals 24/18. And I do need to simplify that, but I'm mostly done because x is all by itself on one side. Let's see, 12/9 and 4/3. All right, alternatively, right, this problem was 2/3 times x equals 8/9. So you could just divide by 2/3 on both sides. You're going to get the same answer. It's just a different way to do it. And if you feel really confident dividing fractions, awesome, use this one. If you don't, great, use the other one. So I have 8/9 divided by 2/3. I'm going to need to remember that dividing is the same as multiplying by the reciprocal, right? My inverse operation. Then I just multiply right across, 24 and 18. I'm going to simplify it a different way this time, just for fun. Divide by 3. And, oh my gosh, it's 4/3 again. When you see a decimal, again, don't panic. Everything's the same. We just have a different number. So we're going to divide by 0.3 on both sides because we were multiplying x by 0.3. And x is 5. Here I've got x divided by 0.4. So to get rid of that, I'm multiplying by 0.4 on both sides of the equation. X is 1.4. If I was subtracting 2.5, I'm going to need to add 2.5. And don't forget, when you're adding decimals or subtracting them, you have to line up those decimal points to make sure your place values keep everything the same. So I can put a little holder 0 right here and add these guys up. 7, 5, 3. So x is 3.57. Now, getting to slightly more complicated problems, you do sometimes need to combine like terms. So when I have multiple variable terms or multiple numerical terms on the same side of the equal sign, I want to make sure that I'm combining them together. Notice back here, I drew the line to remind myself to do the 2 plus 2.5 on both sides of the equation. I wanted to make sure I remembered to do it on each side so that I don't imbalance it, right? But back here, that 3x and that 5x are on the same side of the equals. So I don't need to worry about doing the inverse or doing it on both sides. All I'm doing is smushing these together. 3x and 5x, 8x. I bring down my plus 5. I still have my negative 11. Now I need to solve this guy. It's a little bit more complicated. I have to get rid of this plus 5. So I'm going to minus 5 on both sides. I've got 8x is negative 16. And now I need to get rid of this times 8. So I'm going to divide by 8. That's my inverse operation. And x equals negative 2. On this one, I have multiple numerical terms. So 14 and 12 can get combined. They're on the same side, so just smush them together. 26 plus 2x leaves me my 30. I'm going to solve this bad boy by subtracting 26 from both sides. 2x leaves me 4. 2 times something is 4. Let's divide by 2 to get rid of that times 2. And we'll have x equals 2. Okay, it looks like a mess, but don't worry, we're going to be fine. On the left side of the equation, I've got 3x and an 8x and a minus x. So I'm going to take these guys together. 3x plus 8x is 11x. And then subtracting that 1x is going to leave me 10 x's, right? 3x plus 8x minus 1x, 10 x's. Then I still have my numerical terms, -5 and -2. So -5 minus 2 leaves me -7. I'm getting even more negative when I combine those together. And we still have 23 hanging out over there. Now to solve, I had x. It got multiplied by 10, and then 7 got subtracted from it. Detective time, going backwards through the problem, I have to get rid of this -7 by adding 7. So I know before I subtracted 7, I had 30. So 10 times x makes 30. To get rid of that times 10, I'm going to have to divide by 10 on both sides. And now I've got x equals 3. Move it over here.